Okay, so let's get started with a replacement microphone in the first place. Good morning, everybody, to the tutorial Faster Python Programs Through Optimization. Very nice day again today, but we have to stay inside. Learn something about Python. Though the room is pretty full, so I think the sign up filled up all the seats in the room, so you need to be signed up to be in the room actually. So we have the whole morning till lunchtime for this tutorial. First I would tell you a little bit about me, then I ask you a few questions about you, not everybody. Don't be afraid to just get an overview about what the experience of the audience is. So my name is Mike Müller, as you can see here, and I'm from Python Academy, and I'm a Python trainer since 2004, and Python Academy exists since 2006. So a lot of my time is spent teaching Python. So we have introductory courses, advanced courses, and tutorials like this. This optimization tutorial I taught several times at PyCon US and also last year here, though that's something always people are interested in, making Python programs faster. Okay, we will go over the program very quickly. I just want to know about your experience of programming Python. So who's using Python less than 1 year? Only a few people. Less than 2 years? Okay. Less than 5? Okay. And more than 5? Okay, so half the people are really experienced Python programmers. So who's working with Python 2.6? So a few people, so it's still interesting. Who's at 2.7? Okay, that's majority. And who's working with version of 3? Only one person with 3. So I suppose we will mainly work on 2.7, that's right, but also we will embark on 3.3 here and there to see where the differences are, if there are any, to see what's going on. Good. Question about operating systems. Who's on Windows? 1, 2, 3, 4, 5. 5 people who's on Linux, some kind of level of Linux. So it seems like more than half the people. And who has a Mac? That's also about 1/3 or so. So about like half Linux, and then the rest, then Mac, and then Windows. So this tutorial should cover all the operating systems. I tried most of the things on different operating systems, and I even have a virtual machine, so if you need to, we can try things out. Because at some places there are some differences between operating systems, and you need to be aware of this, because you never know where your program is going to run. And then there are some subtle differences between operating systems. Okay, let's have a quick run through of the program. So we have 3 hours and we have a lot of things to cover. So first I have a full overview. I will talk quite a bit about the principles of optimizing. So the first we answer the question, how fast is fast enough? And we have some optimization guidelines. After this we go into strategies, how to do things, and the very first thing is to measure. So measuring is very important in Python, and therefore we spend quite a bit of time measuring. And of course we measure and profile CPU usage, which is important, but also we have a look at the profiling memory usage, which is not that common maybe, but might be a problem if your program uses a lot of memory over time. Maybe then you want to profile memory. And after this, after the profiling, we assume we have a problem and we need to make things faster. And there are different strategies making things faster. First, we start into small. So we look at algorithms and anti-patterns. String concatenation is a hard one. Lists and generator comprehensions, and something about scoping, global and local variables, those kind of small kind of things. Then we look at data structures. Very often, if you use the right data structure, you get the algorithm for free. It comes with a data structure in Python, and you can get quite a bit of speed up. And then we have different techniques. We look at caching, then testing speed, and we look at an example. It's a computationally expensive example we use, and we work through this. Is simple, but good enough to make the point. And we look at different things. So people that are on 2.6 can use Psycho. So it works only with 2.6. And then we have a short look at PyPy. So we don't do much with PyPy because it would be a whole topic. I just give the information that PyPy exists, and you just replace Python with PyPy. Then we have a short look at NumPy. So this is something from the scientific community in Python used quite a bit. You might not be familiar with it. Just also NumPy is so you know it's there. And there's NumPy, and we also look at using multiple CPUs in Python, which is a multiprocessing module, so you get some feeling how the multiprocessing module works, because Python itself, if you run it the normal C Python, it cannot take advantages of threads for CPU-bound tasks. So for other things, it's nice, it's fine. If you input-output, then it's good, but here you need to use multiprocessing, you see how it works, and then we combine different strategies. So this is our the overview of the topics. There's more, but we don't have so much time, and I rather cover these topics in a little bit more depth and touching even more topics, because there's a lot of things you can do extending Python with different languages. So leaving the Python world and going to C or even Fortran or whatever. And there's a lot of technologies out there, Python and so. But Python now we have a Python course in the program with a Python core developer, and we start with 1 day, now we 2, and we have to extend it to 3, because there are so many things you can do with Python, and it only works if you do exercises, because you can also combine Python and NumPy. So there's much more than I can show here, but I think it should give you some feeling for it, and introduction, and how to continue working. So it would be good to have the microphone soon, because I want to type, and I cannot type and hold this microphone at the same time. So that's a good thing that we may have some. I talk a little bit. So in the meantime, you can download. This is a sample code. It's a very small file, and has a few Python files we're going to use, so you don't have to retype it. So everybody of you should have a handout. So everything we cover is written in the handout, and the handout should be good enough for you to work through after this tutorial. Pretty much everything what I say is written in the handout. It's like up to 80 pages, something. It's 78 pages or something. So it's pretty substantial. Yeah, over 80 pages actually. Yeah. So if you look there, and all the code is also printed there. So even if you don't have the zip, you can retype the code. It's not too much. It's just a few lines here and there, but it's more convenient to use the code from here. And it's written for 2.7. So who's on 3 might have to put some parentheses around after the print statement. Those is the most important thing. Most other things should work, and a few things I tested on Python 3 here and there, and I tend to use for newer code from future import print function. You might know about this, and then you can use the same syntax for Python 2 and Python 3, and then that shouldn't be a problem. So it should work with Python 2.6 for sure, I guess, because this tutorial exists for a while, and I tried it with other versions. Okay, so that's the download. If you don't have it yet, I will show it here and there later on. So it's just pythonacademy.com download EuroPython EP 2013 optimizing zip. Pretty small file. At least I uploaded very quickly, so it shouldn't be a problem. Good. So since I changed microphones now. Okay. So can you still hear me? Yes, it sounds a bit different, but still me. So okay, let's continue. The beginning, I will tell you a little bit about the general thing of optimization, and later on we do more interactive sessions. So when I type some code, you are welcome to type along if you feel comfortable with it, or just watch me. It depends on your preferences, and you can try things. We have a few exercises in here, but I guess these 3 hours we don't have much time to cover the exercises, but each exercise easily takes like 20 minutes, half an hour. When we have 5, 6 of them, then just do the math, it wouldn't work with the tutorial. So we have this handout, and I just go to the handout a bit and show you a few things in the handout. It doesn't go to the... Yeah, okay. can go through here. That's a handout, and so I wrote it down really in formulated sentences, so you can read it's not only bullet points. That should make sense. Okay, let's go through the warm up in the morning before we actually do some typing ourselves and try things out. Optimization guidelines. The first thing is premature optimization is the root of all evil. Very famous saying here, and I think that's important, even though I teach optimization, but very often you might not need it. So it's a big question. You're in the beginning before you do anything. You have to answer the question: do I need optimization? Do you need optimize things? And then if you say I need it, then you have to find the right place where to do it. So Python is interpreted and has a reputation of being slow, which can be true at certain places, but in many places it's not slow. For a lot of things, actually, it's pretty fast. So if you do string processing, Python can be pretty fast. If you do input-output, Python can be pretty fast, because most of the things just delegated to C anyway. And if you rewrite the thing in C, you wouldn't be much faster, likely. So it depends very much on the case. But a lot of things are fast, like the people that wrote Mercurial. Mercurial is a distributed version control system written in Python, and they use this Python to read and write binary files, and they're pretty happy with it, because Python is pretty fast for this. So there are some applications Python is pretty good. Where Python is really slow is for numerical applications. So as soon as you do something with math, with heavy math, then Python gets really slow. And I mean a factor of 10 or even 100 slower if you do the same thing in C. That has to do with because everything is an object in Python. And if you treat an integer as an object, and every time you add two integers, you have to ask them to have an add method. And what you do with the add method and do something with the add method, that takes a while. So it takes much longer than just adding two integers in C, for instance. That's a big thing if you do numerics. That's why there's a lot of solutions for this. NumPy is one of them. We're going to look at them. So if you do numerical things, then if you do a lot of them, then it's likely that you need some help from somewhere else. If you do other things, it's not that clear. And that's something we want to look at. So before you really start, you have to really look at, do you have a case? Do I need to do optimization? Does it make sense to optimize, spend a lot of effort, and maybe gain a little or nothing, yeah, after this? So make sure it's really too slow. You have to really make sure your program might be 10 times slower than a C program, but the question doesn't matter. So you have to see the context of your program, what you use it for, and the end, in the whole context, the whole thing, does its slowness is this a problem or not? And this is very difficult to answer. You have to measure, and things might change over time. Those things that might have been a problem before change because you add way more things to your program, and other things make it are more important than the things. Like if the startup time of a server is slow, if you start it only once in 3 months or so, it doesn't really matter if it takes a minute or 3 minutes to start your server. So you probably wouldn't spend 3 weeks to optimize the startup time. If you need this for development and need to reach started 10 times an hour, that's a different thing. So this is always a perspective you have, what you want to do with it, who's using it, and those things might change over time. Then another thing, don't optimize as you go. So you shouldn't optimize as you go and say, okay, instead of this 1 line, I write 5 lines because that's likely to be faster. Just don't know. So I do this for quite a while, but sometimes I'm very surprised that things are slower or faster, and of course you look at it and say it must be faster, but it's not, and then you try to measure, and after a while you say, okay, it's very clear it's not faster, but you don't see it very often. And that's our small, rather trivial program. If you have really difficult programs, then you don't see, very often you don't see what is fast and what is slow. So don't optimize. We have something, we make Python programs more Pythonic, and the side effect often is that they get faster. That's fine. So if you make more concise, better understandable programs, and at the same time they get faster, that's the ideal solution. But optimization often means making your programs less readable, adding code, doing things. And if it's getting less readable, more complicated, then you really should step back and look at it and say, do I need it? That's important, and very often you brush over this step. You're tempted to do this, that's like this. But still you should go back and say, do I need it? And only use realistic use cases. That's what I said about startup time of a server. If the startup time is very long, but you rarely start your server, it doesn't really matter. Or if your application it's an internal application and you know your company only has 10 people and there won't be more than 10 or 12 people working with it, you don't have to scale up to 10,000. It doesn't really make sense. So if you need 10,000, you might need a different application anyway, because a lot of other things are more important than optimizing things. So that's something you have to find realistic use cases. It's not that easy. Things are changing over time. And it's just a question if you design from the beginning on to scale up very big, then the design might be a lot of more work. So this optimization in the design, it's just a question if you need it or just throw a thing away and write it new. That's something you have to say. The architecture is very important. So we're going to look at some more small scale things here. But if you write a real application, how things work together might be important. That's something difficult to teach in a tutorial because we cannot write a gigantic application, obviously. So, but architectures you can see as one kind of very big algorithm. Sometimes there are bugs in there. So first you have to make the program work right before you make it work fast. So sometimes people forget the print in the inner loop or something like this. So you do print debugging, which is we can do. But then you forget something, the print or sleep in the inner loop, and things are slow. Or you have some bug, something is wrong anyway. You read a file again and again and again, and then you wonder why it's slow. Because if instead of reading a line, every time you read a line, you open the file. That might happen because somehow you don't see that this happens. We call something from there, and it's not that obvious. So it's always good to have tests. Actually, when you do optimization, you have to have tests because you change your program, and you want to make sure the result is the same. You don't want to change the result, you just want to make it faster. And as soon as you change the code, it might happen in Python, you just mistype a variable name, and it might still run, but it has a different result. And if you don't test, you introduce bugs. So that's very important to have tests for what you optimize. So no bugs. And then, if a program, that's a rule, if a program is slow, not the whole program is slow, very likely you have some bottlenecks. There might be a few exceptions, but very often you have bottlenecks, just a few places where things are slow. And then you have to find them and you put your effort there. And that's not that easy, but we will use profiling to do this. Of course, it always checks the results. You have to have unit tests or tests in general, unit tests or functional tests, so that your program is still doing the right thing. And as I said, algorithms are, most of the time you can get orders of magnitude speed up changing the algorithm. Is your algorithm that you use is the wrong one and you can change it to a better one, it can be 1,000 times faster. We have some examples. So that's something possible. Doing other things like writing things in C or other languages, depends what you're doing, might not give you that much of optimization. Okay, that's some guidelines, and I think they're important. And also, if you look at it, not very often the thing runs slowly, but Python might not be the course. There are a lot of other things involved that Python doesn't have anything to do with it. Like if you have a network connection, if you wait for a network connection, it doesn't really matter if you wait slowly or wait fast, you have to wait. So if you write it in a fast language, you still have to wait. If you write it blocking or something, so you might have to consider changing the strategy and just write something that doesn't block or things like this. But it has nothing to do with the execution speed of Python itself per se. Database access is the same thing. A lot of web applications, the database is a bottleneck, and you can tweak your Python as much as you won't make the database faster unless you change the SQL query generation or something like this. Calls to the system, so the thing is a print. Yeah, so if you add a print, also depends on the operating system. I think on Windows print is slow. If you add a lot of prints, you can make a program that runs a second, run a minute, because it prints a lot of things, and the print speed is expensive. You have to generate a lot of things. So that can happen. If you call this a system, then the system might do it uptime, and you don't have too much leverage over improving your Python, making things faster. So that's a lot of things. And also, sometimes memory and speed are connected. So if you use too much memory, and Python is swapping things out to the hard drive, then things get really slow. Then pretty much your program code kind of stopping. You lose a lot of performance. That's something I want to show. Okay, so there's a few books here I cited, so you can look at them. They give you some ideas. Then the new cookbook from Alex Martelli. I haven't looked at it. I just ordered this. Has a few things though. No, it's not from David Beasley, the new cookbook. There are some Python cookbook. You might know this book, and there are some recipes here and there for making things faster, which is always interesting for use case because obviously we can only cover the general idea here. Okay, that's setting the pace for the day, and let's have a look. So if you want to measure things, there's different ways of measuring, and the first thing is measuring in stones. So you have this in this lib. You see, you have here for different versions of Python, and somewhere in this Python lib directory, and they have the test module, and then you have the PyStones, and these PyStones can be run. So I have here I'm probably gonna use a. Who's familiar with the IPython notebook? Yeah. So I'm going to use it here because it's very nice for demonstrating things. If you have a problem, you're welcome to use your own thing, and if you have a problem, you can also fall back to the normal interpreter. I tried it several times in courses, and has some very nice advantages here, but also a few things that might not be obvious. I'll explain. So if I just call IPython notebook, then Python will offer. So I have this. Yeah, so I have this website. Okay, it opens here. So if you have IPython installed, you can install it with, and IPython notebook has a few dependencies. So if you don't have it, doesn't matter. It's just gives you the same functionality as normal Python, but I can use IPython. Just a minute, I'm in the wrong directory. I want to go to a different directory. Okay, and now start the IPython notebook, and this opens a new notebook in the browser. This gives me the advantages. Has the advantage of having an interactive prompt and some kind of persistent thing at the same time. So that's the IPython notebook. So now I can say import test, and this is a test. You see that comes from by Python 2.7 installed. That's a Mac though, and the Mac tends to put this install this is very deep. And then in Python notebook I can use this question mark, and it tells me what the test is all about, this test module. And if I say dot tab, it should give me, why doesn't it? Ah, yeah. Yeah. And shift enter. Shift enter. Shift enter gives you the PyStone. So that's what I just, if you can, there's a PyStone script you can run directly. That's what I'm doing now here, main, and this gives you a feeling of the performance of your Python installation combined with your computer. So I used to run this with different operating system in a virtual machine and stuff, and this is some kind of measure you can use. So if you need to run your program in different places, there's the same thing as running the Python.py from the command line. If you import test, though that's the reason never call a module on your own module test, because Python standard library has a test in there, and then you might get some strange results because it's taking the wrong test likely. So and that's some of those bugs that might be difficult to find because you say it's there and it doesn't work. And so let's test, and then you can use PyStone, and it gives you a PyStone. You see that's how many PyStones per second I have. You will get probably a different result depending on your hardware, on your Python install. So you can try to do this for different Python versions, and you can also do this for PyPy. We will look at PyPy later. If you do it for PyPy, this will be quite a bit faster. And you can do it with JSON, you can do it with EuroPython, and other things. So if you just run this thing, so if you have this file here, and I just go to the console, and I just say PyPy, which I have installed, and run the same thing, PyStone. Yeah, PyStone. So it's just the same file. You see, now I have it's 522,000 compared to 65,000. That's about, I don't know, 8 times faster or something. Yeah. So you get way more PyStones per second using PyPy than using CPython. But that's a benchmark, you know. Benchmarks, you could say, big lies, benchmarks. No, benchmarks are always targeted to something, but this is a benchmark that comes with Python, and that's the best usually you have. And the benchmark thing that about the supercomputers, they still use very old benchmarks, but they don't have anything better to compare things, and that's just, it doesn't mean all your programs run so much faster. It's just for this selected cases, the things are faster. And if you run this with JSON, it will be slower, quite a bit slower. If you run it with EuroPython will be like twice as fast as CPython typically. So I cannot run EuroPython because it's not a Windows machine. So you will see that gives you some kind of measure. We use it later on to work with PyStones. We also have an example here. So if you go to the directory, is it EuroPython? Yeah. So we have this. If you had a zip file, if you unzip the zip file, you will find this directory. This untitled, not because I just put it there. So this is a directory, and under the measuring, you should find the file PyStone converter, and this is a small helper we're going to use later on. And this one helps you to convert PyStones to something you can use. Because the number is so big, I use what's called kilo PyStone, so I divide everything by 1,000 here, and I use the runtime actually takes and multiply with PyStone. It's a kind of a normalization, so if you run your program in different Python installations, then you can use this. So this is just a question if you want to do it, but it's one tool you can do. So later on we're going to measure runtimes in seconds, and if you want to normalize it somehow, that would be one way. If there's a best way, that's questionable, but it's one way to do it. Just as a principle, just you get a second of runtime, and this is a benchmark time in the PyStones. This is what we just did. Yeah, just this gives you back the tuple with these two numbers, and we use this PyStones and convert it to some kilo PyStones from seconds. So, okay, let's embark into the profiling. So, assume we did all the steps, we figured out our application is too slow, and we have a problem, and it's likely Python, and now we want to find the bottleneck. So, as I said, most of the time, you have some kind of bottleneck, and you want to focus on the bottleneck. If you don't have a bottleneck, it's very problematic, but if you have one, you can just say, okay, there's 1% of the code that makes things slow, and I want to go there and make it fast. The rest doesn't really matter. Very often you have something like this, but you have to figure out if this is the case or not. And there's a module called cprofile that comes with Python. There's a normal profile in Python, which is written in Python, but adds a lot of overhead. The problem is profilings, you measure something, and every time you measure something, you change your system. So you don't really measure the real thing, you measure the system you influence already. As long as the influence you add is small compared to what's happening, it's okay. If you add 100 or 200% overhead with your measuring, it might be a problem, because your measuring might have more impact than the system itself. And it's pretty hard to tell those things. So you have to try. There are some things we can do, but you have to be aware that your measuring might be off, your measuring principle. So the measuring itself, you change the system so much that you get a very different result. So the profiling in there's one called hotshot, which is not in the standard library. You don't use the UC profile, which is, as the C indicates, written in C. And we can do profiling. So, okay, I have a very small profile me file. It's profile me here. If you open it, it's a very simple file. It just has a few functions inside that wait. This is fast, that waits 1,000 of a second, and this is slow and waits hundreds of a second. So I use a time module. Time module has a function sleep, and sleep just stops. So here obviously we measure only what's called the wall clock time, so the time that really elapses between the start and end of a function or something. So not the CPU time. We'll have a look at the CPU time also. So that's our functions, and then we just have two other functions that use them. You write a loop for 100 times. So that's x range. If you use Python 3, just delete the x, otherwise you want to run. So we have these loops, and then we just run the thing, and now I can just import it. So the easiest thing now, though this EuroPython notebook is the same as I would work with the interactive you see, this gives me a nice call tips, and I have to type enter. A tab. If you put the period, it gives you the dot. It gives you the thing in the tab. And now if I choose enter, you go to the next one, and shift enter gives you this one. See, I'm here now, and now I want to change to this measuring directory, so it's easier for me to import things. I don't have to, because there's not packages, just single files. So it just very simply change there. So okay, and I say okay, and I can check again. See, now I can go back in time here and can do this again, and I'm in measuring. Note, that's something I need to show you. The sequence you see here is not necessarily the sequence is executed. You see that has the input 8, output 8, and this is input 9. So this one is older than this one. So you have to be a little bit careful, because I just jumped back. So this is these numbers show you in which order I executed those what's called cells. But now I changed back. You can, if you don't like this, you can always move those cells. You just go to cell, and you say cell. Edit. Move cell down. Yeah, so you can move the cell down. Now they are in the right order again. You have the 8 and the 9 here. You see 7 is missing because I don't have any input anymore, so things can happen. You can also rerun all the cells if you like to then. Which will be won't change it. Sometimes you will have strange results if you rerun things. Okay, that's just the thing about EuroPython. Now we are in this thing, and now we can import profile me, and we can import C profile. The C profile is this module in Python, so you have to type it right. There's a P. The C is lowercase. Yeah, that's even true on Windows. So on Windows is strange because Windows is not case sensitive but case preserving. So that means upper lowercase doesn't matter, but it does matter. So that's kind of very strange. Okay, here on Macs and Unix, Linux systems, it matters anyway. Okay, now we have this module C profile, and now we make an instance. So I call it instance, a profile, instance a lowercase, C profile, profile as a class, obviously. Now we have this instance of this profiler, and now we can use this profiler to do all kind of things. This profiler offers quite a few things. We just look at a few of them. They're all very similar. And now this thing is going to profile things. Actually, here in this interactive thing you can do even more, but I show you the traditional way, because this has what's called magic. This EuroPython is doing this profiling and importing this profiling in the background. But I just say run call, and then I dump in the function I would like to run. Profile me is a module, and in this module we have this use fast. Yeah, profiler. You see, and I can go back and correct it. So now I have this profiler, and it's running it, and since it's fast, it's fine. And now I can ask my profiler to give me the results of the profiling. Profiler print stats would be the easiest thing to do. And this gives you some information what's going on. You see now, I get a short overview. Our program is very simple, that's why it's very short. If you have more complex programs, you get many more lines. You have to look at. See, now we have some output, and it gives you time measurements. This is per default, what I said is a wall clock time, so the real time it took to run the function, not the actually used CPU time. And then you can see where the time is going. And you have the number of calls. This function is called 100 times. Yeah, and then you have the call per function, and since we just display 3 digits here, decimals, you don't see it, it's so small, and then takes 0.1 second. That's how long. If we sleep, we slept a thousandth of a second, yeah, that's per call, a thousandth of a second, and you do this 100 times, you end up with this number, and the other function just calls one and has the same total runtime, because the overhead calling the other function so small it doesn't show up in our results. Okay, so that's some statistics. Some interactive ones you will see later on. You can dump everything in the file and do some later analysis of this profiling. That's a basic thing. You can also now do, instead of saying profile fast, we just say profile slow, and then we should see a different result. So it should now it takes a while. You see the star means it's still working, yeah, because now we are quite a bit slower. It takes more time, and now we are done, and we can use the same call now with the stats. So this is cumulative. It just has the old stats and new stats in there, and you see we have the stats we had before and the new ones, and then you can see this is 10 seconds. Yeah, if you wait a tenth of a second 100 times makes 10 seconds waiting time. Yeah, that's a little bit more. As always, when you measure time, it's not accurate, and if you keep measuring the same thing with high accuracy, we always get slightly different numbers. That's very common. Therefore, we will see that on there's some other tools that usually don't measure only once. You do it several times, it takes the fastest. This one approach takes the fastest. You can really see how long it takes. Other approach would take some kind of average to see what would be a normal case. So that's something you can do with a profile me. And you see how we call this here. We hand in the function object. Yeah, the function object, and this one is called here. We can also instead of using run call, we can use this run, and then we can just dump the expression in there we would like to run. So instead of saying run call, I just say run, and now here I just, as a string, I put in what I would like to run. So that opens a lot of possibilities, because you can generate the string on the fly if you like, and this would give you a lot of possibilities to adapt this profile, to automate this profiling some way or the other, because you just can generate a string. automatically and can test a lot of things. So this should gives you the same output now. See now I get the same result from here directly as a return. And I run this one, I don't have to say print. I get this output, and you can run this. You can also store these things in a file, and we'll see later on that we can use some tools to visualize. So if you don't want the output directly here, you just supply, maybe I copy it, it's easier. You can see it later on. You just supply a file name, and very often you call it some extension stats, fast.stats. Supply a file name and run it, and then you can look inside the file if you like to, but it's binary and it's not very interesting, but there are a few tools that help you to look inside later on. So you can do this in your program, store those results in a file, and later on you import what's called pstats and uses module pstats and the class stats and open the file. So we just dump the file in the current directory, so we can open it from there. Stats, and now we have stats, and this stats has a lot of things you can do with it. We just look at some basic ones. See, there's a lot of things you can do here, and I've just say print stats, and it's printing the stats. So that's doing the same thing, but with an advantage, you can store things in files. So you can put this in your program, let it run for a while, and later on do the analysis, and everything is stored in a file. And then there's a lot of possibilities there. What you can do with this thing, you can sort it by, for instance, instead of saying print stats, you can sort things. So there's quite a few analysis things built in. You don't have to do it yourself. You just say sort. You see sort stats, and you want to have it. You want to have it sorted by calls. Then it's sorted by how many calls are done here. And then you can limit how many you want to print. For instance, you get something back on this object. You can call print stats. And you say, I want to have only the first 3, or something like this. So there's a lot of things you can do. So now it's ordered by calls. You see that there are 100, the biggest numbers are here. So it's descending by per default. You can adjust all those things, and you can print things. You can also, if you don't want to print by calls, you just say time, and you print it by time. Everything's printed by time. And now it's... Yeah, this it's the same that fastest first, so that there's a time, and if you take the three away, you see all of them, and it should be sorted by time. You see that's a time here. Yeah, that's a time, and it's sorted by time. That just coincidence with the end calls here. So that's something you can do, and you can also figure out who's calling whom. So you have this this notion of a caller and a callee, and then you can figure out these relationships by saying stats print callers here, and this gives you callers, and then you just say, okay, give me the fast. So and that gives you this information about these callers. You see now you have this arrow here and you see where this comes from. This is a function itself, and there's a use fast, and you have the information. This function was called by, and you can see who's calling it. So that's some interesting information. We will see later on that you're not constrained to textual output. There are some nice tools that visualize those things. Very often here visualization can give you a lot of more condensed information. Okay, next topic I mentioned already. It's the question of the wall clock versus CPU time. So it's called wall clock because it's like the clock at the wall. You see the time elapsing. And that's what we measure per default. And that's very often what you want, because you are interested how long your programs run. I start here, and after an hour I'm finished. But sometimes you also, especially if several programs run on a computer, you're more interested in CPU time. Maybe your program is waiting most of the time for input and doesn't do anything with the CPU, and you can use the CPU for something else. Yeah. So that's the other thing, CPU time, and this is not that easy, because it took me a while to figure out how to do a good CPU time measurement. And I have a small helper function here, a small helper function, and the small helper function is a CPU time. Is it CPU time? No. I have forgotten the file name. I should write the file name here. I just modified it lately. Clock check. Yeah, that's a clock check. Okay. See now here, this is, maybe you're familiar with from future import print function. That means if you do this, then you can use the print function in Python 2. So if you're with Python 2.6 and better, it's recommended to do this. Then you can use a print function, and you don't have to convert anything when you switch to Python 3. And I realized most of my programs, it's just the print functions that I have to change. As long as you do anything fancy with Unicode or so, that's often enough to make it run with Python 3. That's what I do here. I need a few modules, OS, time, and timeit. Timeit is for measuring time. We can look at it in a minute. And now I just try to generate some synthetic use case to make the difference between wall clock time and CPU time. So I use here different methods to measure the time. So OS module has this times function, and this gives you different run times. If you do this, you get a tuple with a lot of different values. So depending on your operating system, you will look different. So here that comes in the difference between those Linux and BSD systems and Windows. So if I say times, it gives me a tuple of different times, so you have to look in the documentation what it actually means. And this is some times in seconds here running, and if I do this again, I will get some different numbers. Just that's the CPU time. The first number, it's interesting, is the CPU time that elapsed. So actually, even though I talked several seconds, the CPU time elapses very little because my computer doesn't do a lot. So if something in the background for this process. So if I would do some more calculations here, then the CPU time would go up much more. So I don't use a lot of CPU time. If I would just check the normal time, it would give me like 5 or 10 seconds, whatever it took me. So that's the difference. But this is the problem if you do this. This shows only 2 significant digits. This is not very accurate for some reason. And that's a bit a problem here on this Unix systems, but on Windows it gives you more precision for some reason. So you have to sometimes be careful what precision you get from where. And then the next one is this clock. If I use time clock has a different meaning between operating systems. Here on my Unix, it gives me the import time, and if I say time.clock, it gives me the CPU time that elapsed. You see now I have 6 digits here, decimals. Yeah, you see now you see it's also this 0.2 sec, but they have way more precision here. If you do the same thing on Windows, we get different numbers. Yeah, so this is just the first time it's kind of 0, and then it always tells you the elapsed time since the last call in Windows. So if you do it again, the number will grow. So it's very different information, and that's why it's tricky to write a program with using time clock that works the same thing on Windows and other platforms. But unfortunately, there's a module called TimeIt, and TimeIt helps you here because it's doing the right thing. It knows about, it's not very difficult, but you might forget. TimeIt, and now if I say TimeIt, that gives me help. TimeIt dot default, there are default timer. If I do this default timer, so this gives me on my Windows, on my Mac here, I get a time.time. If you do the same thing on Windows, you will get a time.clock. So this time.time gives me this elapsed time, always a timestamp, which is pretty accurate on Mac systems. On Windows, unfortunately, is pretty inaccurate. The accuracy is not very high, so it's often not usable for time measurements. So you should use time clock on Windows and time on Macs or Linux, but you don't have to remember if you use default timers doing the right thing. So if you measure time, you always use TimeIt, not time. So it's a lot of times, yeah. So if you use TimeIt, then and use default timer, then you do the right thing. So if there would be even another platform somewhere, but I'm not aware of it, that would do it differently, then probably would end up in TimeIt, and the default timer is doing the right thing. So that's what people call the leaking abstraction. You try to abstract away the operating system, but this is just kind of a thin wrapper around those functions that the operating system offers, and here unfortunately they have different meanings, and that's why we have this timer module that tries to abstract the things away. Okay, now I use those ones, and now we can see what we measured, though that's very important. Though I have this one, see I use these 3 different versions. That's the OS times. The first entry gives you this CPU time, yeah. Up here, so the first entry. Then you use a time clock and you use a default timer. That's the 3 one I introduced. And then I do something a million times, add 1 + 1 a million times, just to first the real time is elapsing, but also I use CPU time. If I just would say sleep, then I wouldn't see any CPU time usage, because sleep doesn't do anything with CPU. And then I do a sleep also, yeah, with the duration I give here, defaulting to 1 second. And then I do the same game again. It's actually the same thing. I just get the current time step and subtract the one I saved before. Just only 3 times. Just put it, you can probably make the code shorter, but I just want to make a point. You see how this how it looks like. So I get 3 timestamps, and then I get the 3 timestamps after that again, and subtract the first one, so I get the duration. And you see this is taken with the OS time times 0, and this is a time clock, and this is a default timer, and I just print out. See, notice the parentheses here, there's a print function. I print it out, and I run it, and you see the differences. So you can run the thing under the command line, and you can see the differences in time. And this is very interesting, because there can be a problem. CD measuring. So I run with Python 2.7 per default, but it should also run with 3. Shouldn't be a problem. So that's 2.7 if you just type Python. And clock check takes a bit, and then you see the different times. You see, if I add the sleep, this is a default timer, measures the sleep also. So this is a 1 second sleep, and this is the time it takes to do this 1 million 1 + 1 operations. And this is what you get from time clock. Here on my system, if you run this on Windows, you will get something different. You should get the same number as here. Yeah? And you see, in this one, it's pretty coarse. So if you look for the small differences here, this might not help you, because you always get difference of 0. This just doesn't give you any result. That's it. But in Windows, this should give you more decimals. It gives you more decimals. I tried it on my machine, so that's what's coming out there. So that's important to know, because once you write your measuring script and it runs, and then you give it to somebody else, and somebody else uses a different operating system, and things behave differently. So that's it might be a problem. So you can, if you want, you can crank up this number to power of 7, so 10 million. Then this time will increase here a little bit by approximately a factor of 10. To see what's happening. Okay, that's what we I think that's important to know this. And now I have this script which is called CPU time, and this is just something I wrote. So this is you see, I made it work with Python 2 and Python 3 and Windows and non-Windows systems. And the first thing is here, this is just some, if you want to run with Python 3, there are some helpers that can do this for you, but you increase dependencies. So just for the small things, I don't want any dependency. Just check if this version is less than 3. I say range is X range. So you might be familiar with this X range problematic here. So I just change range to X range. Okay, and then I write a small function, CPU time, and now here I actually check if I'm in Win32 platforms. This is this Win32 doesn't have anything to do with 32-bit. If you're in a 64-bit Windows, it's still called Win32 because it's the API version of the operating system. So it's still the same. So it's still called Win32. Yeah, so that's something people say, I'm on 64, it doesn't work. You will see this if you're on a 64-bit Windows machine, it still gives you Win32 as a platform. So if it's like this, then I use this, otherwise I use this. So it's a similar principle what default time was doing, just for this here. And then if you do this, now I can use this function. Now I will just write the same thing we did before. This is just this, now I say 100 million times, adding 1 plus 1. You see, sometimes I use this underscore because I don't use this variable actually for anything. And then I run this one. This sleeps 2 seconds and this is doing something. So this is using only wall clock time, and this is using also CPU time. And then I run this thing to the profiler. Because what you can do with the profiler, this is how we used the profiler before. We make an instance and we just dump our test function in here, which is doing this. That's what we just did before interactively, the same thing. And now I give it this function and tell it, okay, use this function to measure the time. So I can actually give it a callback, what is called. So I give it this function object. Everything is an object in Python, so I can use it as a just normal argument in this call, or in this constructor here. Yeah, and then I give it this function, and then now it's using this function instead of the built-in default timer function. And you can do whatever you like, yeah, but you have to be careful, otherwise you get strange results. And now we use this function we just defined and measure CPU time instead of wall clock time. So that's the best I could come up with so far. I haven't found anything else. If you find something that's better, it would be interesting. But this is something that works. So you have some CPU time, and if you try different operating systems, you should get some results with like 6 decimals of the second. This should be fine. So you just run it. So if you go to the command line, and if you say Python CPU time, then yeah, it does a little bit because I do 100 million iterations, and I wait a few seconds, and now you get this dump from the profile, and you can see how long it takes. This is the second one, so I'll try to put it on one screen. See, now we have this, the first one was the one with the normal one. You see this times here. And then compare here. This time is actually 0 because this is the one that just sleeps here. Sleep, you see, the sleep doesn't consume any CPU time. But here it shows up as 2 seconds of sleep. So that's the difference. Yeah, if you look at it carefully, you see the difference. The other times should be yeah, see, also here, this 2 seconds, it's here 6 seconds, only 4 seconds, because those 2 seconds are missing, obviously, because it's only measured with the real CPU time, the CPU is used, and not the time you wait. And that's a big difference. And you have to be aware of this. And this now runs also with Python 3, I hope. So if I say Python 3, that's Python 3.3 here, in my case, and it's doing the same thing. And I think it's a bit faster even. I'm not sure. No, it's slower. For some reason, I'm not sure why. It's 2 seconds slower. for some reason. Pretty much. Maybe I'm something. Do I something differently? Okay, so yeah, I have a few different, you can try play around yourself and see, but this is important. You have to be aware of what you're actually measuring, and that this is you see this very, very small system, just four small functions with one line each or something, or two lines. If you have a real system, it's much more complicated, and you might get lost very quickly what you're actually measuring, what's happening. So it's always good to do some experimenting, to step back and say, does it really make sense what I'm measuring? That happens. Yeah, that happens to, what's the story about this financial thing, this Excel spreadsheet. They had this big publication, then they realized they forgot 4 lines, didn't put in the formula and didn't recalculate. Those things happen to very distinguished professors. Though that might happen to you, that you measure something else that then you think you do, and you should always do a step back and look at it again. Yeah, that happens to me. Even if it's so simple, you can get tangled up already, and if it's more complicated, it's much easier. Okay, that's about measuring. And now I said we always have this nice textual output. There are some nice tools in Python. I don't know if you got it installed because you need WX. It's called Run Snake Run by Mike Fletcher, and he wrote a very nice tool in WX. Built some other tools, and he can visualize. Those output files we just generated. So we generated a few. No. Yeah. So we generated this fast stats file before, and now you can actually tell this run snake run. The command is run snake, and you just give it the fast stats, and it's generating some nice graphs out of it. This is a very simple graph. If you do more complicated graph, it looks way more complicated, more powerful. And you see this one is spending all the time in this sleep function. If you go here, this is pretty much the same information we get from the textual output, but just nice in a table. And you can arrange the columns, everything. And this is a corresponding graph. And this looks very simple, but if you have a more complex thing, I run our NumPy version, so it get a much more colorful thing. And now you can go there, and it gives you all the information, and you see how things work together. This is very obvious that all the time is spent in the sleep here. So if you go here, you see it's highlighting where you are, and it gives you all the information we have. So this is the same information you have as a table, but much nicer visualized. So if you have a more complicated system, let's look at this more complicated. So if I have it here, I generated from NumPy. Yeah, so that's one we just looked at, and this is a version. It doesn't really matter what the details are now. And this is a version you generate if you use a NumPy, because NumPy is calling to this library, and this library is doing a lot of things. And you see how these function calls are interconnected, what's happening, and where the time is spent. You see, okay, this big area, it's a lot of time. It's worthwhile to do something. It doesn't make sense to do something here, obviously, because you won't gain a lot. Even if you reduce this to tens of the size, it doesn't matter if it's because it's small already, or here you spend time. But a lot of things that you can really influence, because most of the things happening in the NumPy itself, so you would need to change NumPy, which doesn't really make sense. And so that would be a very rare cases that you go in there and change NumPy. Yeah. So this is something you can see, and you can click on all of them and you see the information, and that's very nice to give you a nice overview, and that's also good to talk to people, to say, okay, that's how it looks like. And this one you can even show people that are not involved in programming, say that's it is, and you say this all the small, they're all the same size, so there's no real, it will be a lot of effort to optimize, because you have to catch all of them. Or I have one very big box, though this is a big box where the time is, we have to make this box smaller, then we get faster. Then we have to put the effort in the box, and then inside the box, it depends how big the function is. If the function is very big, then you still don't know. There are things are in this box. You want to make the whole box smaller. But it's a good, nice visualization you can do, and it gives you a lot more information than just doing it. So that's brings us to the next problem I announced already. So far we used functions that are very short, but in real life functions tend to be a little bit bigger. And as you can see, this profiler can only work on a functional level. So the smallest unit it can resolve is a function. What happens inside the function is opaque. You cannot see anything with the C profile. But there are a few tools, or one tool I would like to introduce. You can do line-by-line profiling. The problem is with line profiling, it comes with a big price and makes your program much slower, because now Python has to do a lot of measuring. For every line you execute, it has to do measuring. That makes things really slow. So it doesn't mean it makes your measuring unusable, because it knows about the time it pretty much it uses itself to some degree. But in general, you cannot use this in any place that you want to go fast, because it makes things slow. But it's a very nice tool. It's called the line profiler. So if you say pip install line profiler, then you get this tool. It's written by Robert Kern. So Robert Kern is very active in this scientific community. He's very active in NumPy and those kind of things. And he's also very interested in performance. And he wrote this nice tool, which is called kernprof. And you just can run this kernprof, and it's doing things. So if you have it installed, you can just say kernprof. You see, it's even a get expansion here, kernprof py, and then it takes several command line options. We just take the verbose one, and we say profile. I have to go to the directory, cdo measuring kernprof profile me. So we just run our file, we use all the time, and then it's doing a few things and doing line by line profiling. It takes a while, as I said, because it adds quite a bit of overhead, but you get a line by line output. Again, you have to take this with a grain of salt, because if this introduces even more overhead, it might change your now we have this in this profile. You have to install. You have to say pip. Look at it. You have to say pip install line profile on page 18. So you have to say with the install. You have to say pip install whatever you use. Install line profiler, and it will tell me that's installed already. So you need to install it. Hopefully it works. Yeah, and then you get this line profiler. And it's strange, you install line profiler, but you have to call this kernprof. So you put his own name in there. And so then you can run it, and now it's generating this file we saw already, and then you can analyze this file as we did before and see what's inside. And this one gives you just a normal output. Okay, we go back here, and I just use the same. So we did this before. We opened the file, so we can use the same approach. So that's what we did before. So instead of using this file, we use this file. You see, that's a file name he wrote in this file. Yeah. So we can use this file and just put this file in here. I had to find it up there, so I go get it back. So slowly, just I will clear up the mess here. Yeah, so import pstats. So importing again doesn't hurt in Python, because Python doesn't do anything. It just gives you another reference if you use a different name. Okay, and I go here and copy so I just here. You see it's already installed, it doesn't need to install, I just pressed enter by accident. Okay. And now you get this one, and you can say stats dot print stats. So this gives you per default enter, it's always different. Per default, the same thing we had before. You see that there's nothing different. It's interesting now when you go into your file and you add some decorators. Who's not familiar with the concept of decorators? Okay, yeah. So decorators are pretty easy to use. You don't have to know too much about how they actually work. You just use them. So we have this line by line here. Let's change this. This ordering is not. Usually I use a different editor, but this has nice and big here. Okay, now we have the same function as before, and the only thing I do is say add profile. And this add profile somehow magically gets in there. And this is a decorator. You could even put it in your normal code, and if you wanted to, you just write your own profile, which is doing nothing with the function, just returns the original function. So that wouldn't be a problem. But we do this, and if we do this now, we tell this line by line profile, go line by line through the things and profile them. No, you don't, because you run it from here, and now kernprof imports it automatically in the namespace. It's not very clean because he puts it in the built-ins and it's there, but it's only for debugging. So you always have to distinguish. If you do something in production, I would never put something in the built-in namespace. If you do it for measuring and debugging purposes, it's a different question, because then you only do it for you and you know what you're doing right in the moment. If you do something with built-ins and give it to somebody else, I don't like it, because people will be surprised that somehow something comes from somewhere and you don't know what happens. If you do it right here and you know what you're doing, that's fine, because you only measure things and you don't do this in production code. So if you do this now, it takes a little bit longer, because now it's doing a line by line profiling. Did you call it with kernprof minus v? Minus v, I've forgotten. I don't know. I have to check it. Minus v gives you. I don't have to print it out. Minus v gives you this one. I have to go. This one. Why doesn't it work? Minus L. Sorry, I wrote it there. So you have to say minus L to make it use this thing. Yeah. So sorry, forgotten the command line thing. So there has, if you use help, it has a lot of command line switches. We don't want to get into too many details, but you have to use minus L to actually enable the profile. So it doesn't do it by default. You have to tell it, use this option and do it. Yeah, so it takes a while. And now you see, in addition, those two decorated functions, you get a line-by-line breakdown of the times it takes here, how many times it got hit, how many times it got called, or this line. Yeah, 100 ones, obviously, because then the last one then stops, and this one is called 100 times in this loop. This is very simple. So if you have bigger functions, of course, you get more lines. And this has a lot of overhead. When you do this, I try to construct a case where I only use functions to compare this time with normal C profile, but still it takes a lot of time. And it's about 10 times slower as C profile. That adds a lot of overhead to your course. So that's the price it comes with, but you can do things, and you can run this with a Z profile and have another test function that's maybe a little bit nicer to see something, because it's our function. We have a file called accumulate, so that makes a bit more sense. Accumulate. I don't know why it's not alphabetically here, but sure. Okay, accumulate, and this is just a simple function that just accumulates numbers. So it's just doing a little bit math, so you can see a little bit about performance. So we have this, you get the iterable, whatever it is, anything that can be iterated. You take the first one and put it here, yeah, and then you go through the rest of them, and you just take this one as an old value, and then the new value is an old value plus an element. So you have this. The last one will be the sum of the whole thing, but you see all the intermediate steps to get to the sum. That's pretty much what accumulate is doing. So you see this numbers just adding, so adding the first two numbers and then adding the third to it, the fourth to it, and so on, and keep all the intermediate results. That is what it's doing. And just do this, and now we run this to our thing, and you can see what's going on. So it's a little bit more code, so you can see some, because it's so simple here. So we run the same thing, but we use accumulate instead of the same options here, but we use accumulate, and then you see the breakdown, what's happening, where the time is, how many times things are called, and where the percentage of the time. You see 22% are here, 24% are here, 22% are here of this time, and another 30 are here. So that's where the time is. And you can now say, okay, this append takes time and this takes time. I might do something about it. I might change my algorithm in some way or the other to make things faster, if it's possible. Yeah, but you get some feeling what's happening in there. So line by line. Yeah. So I have a few more test functions here. What you can do with measuring of CPU times, like you can measure how much it takes to assign variables and also the difference between local variables. So I have a few, let's quickly go there and have a look at the code. This would be the calc, yeah, this one directly here, calc. So it's just very simple. I just do something in the loop and add something, add plus 10, multiply by 10, the power of 10, then use the built-in function power. Here instead of this one, use mass, square root, and I use square root as because I set this one here. And also the access here to this, only the access to the attribute, and then just access in the local namespace. So that gives you some interesting results. So you just say calc, and you go through, and then you see where the time is spent, and this is very interesting. You see here, obviously the power is pretty expensive. Yeah, the power of 10 costs much more than multiplying by 10. Obviously, the numerics are more involved here, and this is the time it takes to access this square root, and this is the time it takes to access mass dot square root. It's a bit different. Yeah, so there's the same. You see also difference if you just do mass dot square root number or square root number. You see there's some difference here. So if it matters or not depends very much on the application, but it's interesting. You get some feeling how long things take relative to each other. See if you can avoid power. So if you say instead of writing power of 2, you can very often can say just x times x instead of writing x to the power of 2, and then it might save you sometimes something if you do a lot of calculations, for instance. That's one thing you can do. And the last one I have here, it's a bit more involved. I do a few tests here and there to see how much CPU is used at these places. Local references. That's an optimization technique we look on later. Why doesn't it go away? Yeah, local references. So I use this profile here. See, and now I do this trick. I try to profile a dummy function. So if this doesn't work, then profile doesn't exist, and I just use I write my own profile decorator, which is a very simple decorator, does nothing, taking a function and just returning another function. Actually, I should use this functool reps. Why don't I do this here? Yeah. Oh, yeah. And this one is doing nothing, just returning. I should use functool reps, so, but it's fine. So this one is just returning the result of this function and returns this function. This is just doing nothing with a function, but I can use the decorator without putting it in and out. It costs you a bit performance because you have one extra function call. But it's not, depends what you're doing, it might be fine. But you don't have to comment out all the add profile all the time. So if you want to experiment, that might be one solution. It's pretty easy. You don't have to do anything. We can use it as is, as a recipe. If you don't understand, doesn't matter too much. But then you just can put this decorator there, and if you don't call it with a -L, it just doesn't do anything. Yeah. And that's just some helper, so because it makes it nicer. Because I tried several times, every time comment these things, that's not nice, so that makes it automatic. So now I have this local reference thing. So here I do this trick. Instead of calling module mass.square root, I just give it a shorter name, a local name, and use this local name here. And here I just call it with a full name. You see? So it's a different thing. And this is one just, they are not decorated, and then I use a decorator. And now I want to have a line-by-line breakdown of this one, and you see what's going on. And I do a pretty 10 million times here. Yeah, that's 10 million. 100 million. 100 million times. I call this function, and I just run it through my profiler again. So current minus L, and this is called it's called local ref. And then you see the difference is what you might gain if you do this local ref gain. Because you have to use quite a few iterations to see something substantial here. Otherwise, you have a lot of other overhead. There's always a thing. So if you work with short loops, then a lot of those optimization techniques we do here might not really be effective because you have other things. But if you do something very often, then you might have a case. And you see now it's still running. I don't know, I used a big number, maybe I should use a smaller number. Yeah, so just don't be so greedy, just stop this one, and I just go and just take 1 million first. I'm not sure, it's just, and do this 1 million, I should be a bit faster. Now it's a bit faster, and you can see here, if you do this 1 million, the difference are not big, 47 to 53, though that's not really a big thing. But if you go up with the numbers, you will see some differences here and there. So that's something, because sometimes you have this gut feeling this should work, but the only thing is you have to measure to see if it works. Because that's usually a recommendation. Use local variables that make things faster here and there, and they may do things, but it's always a good thing to go in here and measure and see what happens actually. It's still the same, so it doesn't change. It doesn't change a lot. Do I have the same result here? Why do I have the same? Maybe I took the profile away. The profile away from here, because it gives me only this one. I need to decorate the other functions also, I guess, to see something. Yeah, so probably I deleted this. No, it's like this. The output doesn't match here, so obviously I deleted the decorators. So you can just, that's easy, just copy those decorators here also, then you see what's happening inside. Okay, Good. We are close to a break, and we're making a break now because we also change topics. And then we go to memory, and then we go to algorithms. And now, if I do this, then I should see more output, and it takes much longer. So if you want to, you can run 100 million over the break and see what's happening after the break. So we have 45 minutes. So we have 45 minutes. So get some coffee. If you have questions, you can ask questions. Some personal question in the break. I mentioned you can always ask questions in between if something is unclear. But if you want to, you can come to me also and ask me questions during the break. So have some coffee, have some tea, have something to eat, and we meet back here a quarter. We start sharp 1/4 past. Thank you.